In this final lecture for our unit on atomic structure, we're going to look at the periodic trends in ionization energies and electron affinities. We'll talk about what ionization energies are, the factors that govern them, how they vary across the periodic table, and examine single versus multiple ionizations. Similarly, we'll talk about what electron affinity means, the factors that govern it, and how it varies across the periodic table. Ionization energy is the energy required to remove an electron from an atom or molecule, though we're just focusing on atoms here. Specifically, it's the energy required to remove 1 mole of electrons from 1 mole of gas. You can write a pseudochemical reaction for it, as shown in this example here, where we're taking a sodium atom and converting it to a sodium cation plus an electron. The ionization energy for this is 496 kilojoules per mole. That's the amount of energy required to remove this electron from the sodium atom. When talking about ionization energies, we distinguish them based on how many electrons have already been removed. For example, when forming magnesium 2+, we have to ionize 2 electrons. The first ionization energy, i.e. 1, is what happens when we remove a single electron from magnesium, that is, converting it from magnesium to magnesium plus. That requires 738 kilojoules per mole. Then we have to remove a second electron. This time we're removing it from magnesium plus to form magnesium 2+. The second ionization energy here requires 1,451 kilojoules per mole. Overall, forming the Mg2+ ion requires the sum of the two ionization energies, that is 738 plus 1,451, which is 2,189 kilojoules per mole. Finally, because electrons are attracted to the nucleus and would prefer to stay in the neutral atom, energy input is required to extract those electrons from the atom. So ionization energies are positive. Ionization energies exhibit some fairly systematic periodic trends. They generally increase as you move from left to right across a period, as shown for the period 2 elements here, and they typically decrease as you move down a group. Let's try to understand each of these behaviors separately. First, why does the ionization energy increase across a period? As we discussed in the previous lecture on atomic radii, the effective nuclear charge, Z effective, increases as you move from left to right across the period. That also means that those electrons are bound more tightly. That accounts for why the atomic size decreases. Because those electrons are held more tightly, it's going to take more energy to ionize them. So the ionization energy is going to go up as we move from left to right. But there are a couple obvious exceptions in this trend that you can see here. The first occurs between beryllium and boron. In that case, beryllium has a 2s2 configuration, while boron has a 2s2 2p1 configuration. It ends up being easier to remove the electron from the 2p orbital in boron than an electron from the 2s orbital in beryllium, because the s electron penetrates more closely to the nucleus. That means it experiences slightly stronger attraction to the nucleus. The second exception occurs for nitrogen and oxygen. The electron configurations are shown here. Oxygen is the first element in the 2p block that pairs up any electrons in the 2p orbitals. We know from Hund's rule that the electrons prefer to spread out across the p orbitals, as in nitrogen, before we start pairing any of them. This means that the first paired electron in the 2p orbitals in oxygen is going to be a little less favorably bound. It's going to experience a little more repulsion with the other electrons. And therefore, it's going to be slightly easier to remove that electron than it is to remove one from nitrogen. And that's why we see this second dip in the ionization energy trend across the period. Moving down a group, the ionization generally decreases. This can be understood simply based on atomic size. As you move down the group, the valence electrons will be further from the nucleus on average, making them less tightly bound. They're interacting less with the nucleus. You might think that changes in nuclear charge Z could play a role in the trend here, but in general, the Z effective is pretty similar as you move down the group. In all cases, whatever changes occur in the atomic charge Z, those will be largely compensated by screening from the inner core electrons, and so the changes in Z effective are modest. Overall, we get a trend something like this, for example, for group 1, where we see the generally decreasing ionization energy due to the increasing atomic size. Here are the overall trends for the ionization energy across the periodic table. This plot shows that the two trends we talked about are generally true. Within each period, we see a generally increasing ionization energy, though we have those exceptions we talked about when we first start populating the p orbitals and when we start pairing electrons in the p orbitals. You can see that again here in period 3. Once you get to the later periods involving D and F blocks, once again things get a little messier, but still the general trends are true. Let's try a practice problem. Sort magnesium, aluminum, and silicon by increasing first ionization energy. So magnesium is here, element 12, aluminum is 13, silicon is 14. Pause the video, attempt the solution, hit resume when ready. Okay, so the answer here is C. Aluminum has the smallest ionization energy, followed by magnesium, followed by silicon. For aluminum versus magnesium, once again, it's easier to remove the electron from the p orbital than the s one when we've gone from just 2 to 3 electrons. That's exactly analogous to what we discussed for beryllium and boron on the previous slide. For silicon versus magnesium and aluminum, we know that the ionization energy is generally increasing across the period due to the changes in Z effective. And so, in the end, we have silicon with the largest ionization energy, followed by magnesium slightly smaller, and aluminum having the smallest. The actual ionization energies are shown here: 580 kilojoules per mole for aluminum, 730 kilojoules per mole for magnesium, and 780 kilojoules per mole for silicon. When we remove multiple electrons from an atom, more energy is required for each subsequent electron that we remove. The reason for this is pretty straightforward. The nuclear charge isn't changing when we ionize, but for each electron that we remove, we end up having less electron-electron repulsion remaining in the atom. And so that means the electrons can be pulled closer to the nucleus, similar to what we discussed when describing the sizes of cations. And the end result is that we get stronger electron-nuclear attractions. Those remaining electrons get held that much more tightly. So it gets harder and harder to remove each additional electron, and we have to input greater and greater amounts of energy. In other words, we have a larger ionization energy. Removing electrons from inner shells rather than the valence shell is especially difficult. In addition to the effects described above, electrons in inner shells experience much less shielding than the valence electrons do. This table here compares the first and second ionization energies for sodium and magnesium, which have a 3s1 and 3s2 configuration, respectively. The first ionization energy behaves as we discussed in the last few minutes. It should increase across the period, so the ionization energy of magnesium is larger than that of sodium. If we try to remove a second electron, however, we see dramatic differences. The second ionization for magnesium removes the second 3s valence electron. So this second ionization energy is about twice as large as that of the first, but it's still relatively feasible. In contrast, trying to remove a second electron from sodium would require taking it out of the 2p shell because we have no more valence electrons. And as you can see, that requires an extraordinary amount of energy. The second ionization energy for sodium of 4,500 kilojoules is 9 times larger than the first ionization energy. So this is why we can form something like magnesium 2+ relatively easily, but you don't expect to find something like sodium 2+ in nature. Let's try a practice problem. Which of the following ions would you expect to require the most energy to form starting from the neutral atom? Beryllium 2+, magnesium 2+, potassium 2+, or calcium 2+? Attempt the solution and resume the video when ready. The answer is C, potassium 2+. Most of these ones I've shown, beryllium, magnesium, and calcium, are in group 2. In contrast, potassium is in group 1. So if we try to ionize potassium twice, we're going to first remove the 4s electron, and then the second electron would have to come from an inner 3p shell rather than from the valence shell. That's going to require a large amount of energy. In contrast, for the group 2 elements, we have 2 valence s electrons, and those can be ionized relatively easily. Let's try another one. Sort the following ionization energies from smallest to largest. So we have the first ionization energy of aluminum, the first ionization energy of thallium, the second ionization energy of sodium, and the third ionization energy of aluminum. And for reference, thallium is down here at element 81. Pause the video, attempt the solution, and resume when ready. The answer is A. So the smallest ionization energy is for thallium, followed by the first ionization energy of aluminum, the third ionization energy of aluminum, and the second ionization energy of sodium. To start off, we'll look at thallium versus aluminum and their first ionization energies. These are both in the same group, but thallium is further down the periodic table. So those electrons are going to be held less tightly. It's going to be easier to ionize the thallium than it is for aluminum in terms of the first electron. However, as we discussed, each additional electron that we try to remove gets more difficult. So removing the third electron from aluminum is definitely going to be harder than removing the first. So we know the third IE is going to be greater than the first IE. Finally, removing 2 electrons from sodium is very unfavorable. It can remove one relatively readily, but the second one would end up coming up out of one of the 2 p orbitals. And so this is going to be the largest ionization energy. Now let's turn our attention to electron affinities. The electron affinity is the energy associated with adding 1 mole of electrons to 1 mole of gas. Again, we can write a pseudochemical reaction for this process, such as chlorine plus an electron forms the chloride anion. The electron affinity for this process is negative 349 kilojoules per mole. Because electrons are attracted to the nucleus, energy is typically released from the system when the electron is added. Therefore, the electron affinity here has a negative sign. At least when adding an electron is a favorable process. In other cases, however, electron-electron repulsion and screening effects may make adding an electron energetically unfavorable. For example, adding an electron to an argon atom has an electron affinity of positive 35 kilojoules per mole. That positive sign means that this is not a favorable process and it's unlikely to occur. And that makes sense for a gas like argon because as a noble gas, its valence subshells are already completely full. It doesn't need any more electrons to try to complete that subshell. Unfortunately, the periodic trends in electron affinity are somewhat less systematic than those for atomic size or ionization energy. Generally speaking, the electron affinity increases as you move across a period due to the increasing Z effective. That extra electron that we're adding can interact more strongly with the nucleus when there's a larger Z effective. The electron affinity peaks for halogens like fluorine, chlorine, bromine, and iodine since their anions achieve noble gas configurations which are particularly stable. For example, adding an electron to fluorine gives it a neon-like configuration. Within a single group, moving down the periods, the electron affinity reflects a competition between the slightly larger Z effective values found in the earlier periods and then having more space to minimize the electron-electron repulsion in the larger atoms found in later periods. If you look down some of the columns in the periodic table shown here, you'll see that the electron affinity trends are not entirely systematic. We can say, however, that certain groups tend to have unfavorable electron affinities. For the noble gases in group 18, for example, the new electron must go into an entirely new shell. It will therefore be bound much more weakly and is usually unfavored. For example, in helium, if we want to make helium minus, we have to start from a 1s2 configuration and add an electron which would then go into the 2s orbital. For group 2, the new electron must enter a higher energy p subshell. For example, making beryllium minus requires going from the 1s2 2s2 configuration of beryllium to a 1s2 2s2 2p1 configuration in beryllium minus. Because that 2p orbital lies higher in energy, that electron is going to be bound less tightly. Finally, for group 15, the new electron must start pairing in the half-filled p subshell. So for example, nitrogen has that 2p3 configuration which is particularly stable. Adding an electron to it would then go to a 2p4 requiring pairing up in one of the p orbitals, and that's relatively unfavorable. Let's try a practice problem. Would you expect silicon or phosphorus to have a larger, meaning more negative, electron affinity? Attempt the solution and hit resume when ready. The answer is silicon, because gaining an electron for silicon will give it a half-filled 3p shell, which is going to be particularly stable. In contrast, adding an electron to phosphorus will force it to start pairing electrons in the 3p orbital, which, as we said, is less favorable. And you can see here that the electron affinity of silicon is negative 120 kilojoules per mole compared to negative 74 kilojoules per mole for phosphorus. In conclusion, we saw that the ionization energy and electron affinity are influenced by factors such as the degree of electron-nuclear attraction versus the electron-electron repulsion, orbital size and penetration effects, screening and z-effective, and the special stability of filled and half-filled shells and subshells. For ionization energies, we find that the increasing z-effective generally drives the trend across periods, causing the ionization energy to increase, and increasing the average orbital size as you move down a group causes the ionization energy to decrease. This means that the ionization energies are generally largest near the top right of the periodic table. Valence electrons are much easier to remove than core ones, and each subsequent electron we try to remove from an atom is harder to remove and therefore requires a greater ionization energy. For the electron affinities, the increasing z-effective generally increases the electron affinity across a period, but then there are trends within a group are less obvious. There's the subtle competition between the effective nuclear charges and the orbital size. The stability of special electron configurations of the anion also impacts the trends.